Hello and welcome. The date is December 27th, 2025. In the fast-moving world of astrophysics, where new discoveries usually render older data obsolete within months, we are witnessing a rare and unsettling reversal. The scientific agenda has, quite unexpectedly, turned its gaze backward, back to an event that technically concluded years ago. We are looking once again at the interstellar object known as 3I Atlas. You might remember the headlines. You might remember the initial rush of excitement, followed by the quiet confusion when the object didn't behave exactly as our models predicted. It passed through our solar system, it was catalogued, and it left. By all standard protocols, the file should be closed. But it isn't. The object continues to unsettle researchers, not because of where it is now. It is long gone, vanishing into the dark, but because of what we missed while it was here. The reason for this renewed attention, the reason we are leading with this story tonight, lies in a comprehensive reevaluation of the archival data. This isn't new observation. It is new understanding. Physicist Avi Loeb has released an analysis that fundamentally shifts the ground beneath this discussion. It is an analysis that strips away the speculation and focuses on one central, undeniable intrigue: the physical material this object left behind. We are talking about the trail of breadcrumbs it dropped while crossing our threshold, specifically the amount of material 3I Atlas shed, how that amount was calculated, and, most critically, what those calculations imply about where it came from. Before we dive into the numbers, which are staggering, we need to understand the stakes. When an object enters our system from interstellar space, it is a message in a bottle. It is a sample of out there delivered directly to here. If we misread that sample, we don't just misunderstand a rock, we misunderstand the galaxy. Loeb's analysis highlights a discrepancy that has bothered scientists for some time, but only now do we have the framework to articulate it. The headline number that is currently circulating in the academic preprints is roughly 10 million kilograms. That is the mass of the material lost by 3I Atlas during its brief transit. Now, 10 million kilograms sounds like a lot. It sounds massive, but in astronomical terms, is it? And more importantly, how do you weigh a ghost? How do you put a scale under a cloud of dust that is millions of kilometers away and moving at cosmic velocities? This is where the story moves from simple observation to high-stakes detective work. Loeb did not weigh the material directly. He couldn't. Instead, he evaluated the brightness of the glow surrounding the object. This is a technique that relies on the interaction between sunlight and dust. It is a method that turns light into mass. If you appreciate deep dives into this kind of complex scientific detective work, where we peel back the layers of the universe one equation at a time, please take a moment to subscribe to the channel. We are tracking this story as it develops, and you won't want to miss the breakdown of the counter-arguments that are sure to follow in the coming weeks. Let's look closer at the data. The core of this new analysis rests on the extent to which 3I Atlas reflected sunlight. When we look at a comet or an asteroid, we aren't just seeing the solid body. We are seeing the halo, the coma, the debris field. Loeb's team looked at that glow and asked a simple question: how much surface area is required to reflect this much light? To simplify this for our visualization, imagine the glow around 3I Atlas not as a diffuse cloud, but as a giant, solid, reflective sphere. Based on the brightness data captured during its transit, that sphere would need a radius of roughly 10 kilometers. A 10-kilometer mirror ball. That is the optical equivalent of the dust cloud. But obviously, 3I Atlas was not a solid sphere of that size. It was a small object surrounded by a cloud of microscopic particles. So, the calculation involves breaking that 10-kilometer sphere into trillions upon trillions of tiny fragments. We have to mentally shatter that mirror. We have to replace that single surface with dust grains so tiny they could fit on the tip of a needle. When you do the math, when you calculate how many of those microscopic grains are needed to equal the reflectivity of a 10-kilometer sphere, you end up with a number that defies easy comprehension. The calculations require approximately 10 to the power of 18 particles. That is a 1 followed by 18 zeros. This is the moment where the abstract becomes physical. We are no longer talking about brightness or magnitude. We are talking about a physical quantity of matter. When one accounts for the average mass of a single one of those particles, based on what we know about standard cosmic dust, and multiplies it by 10 to the power of 18, the total mass comes out to around 10 million kilograms. This is not a guess. It is a derivation. It is the result of a specific chain of reasoning that links the photons hitting our telescope detectors to the physical atoms shedding off the visitor. But here is where the mystery deepens. 10 million kilograms is just a number on a page until you place it in time. You see, space is not a static environment. It is dynamic, violent, and constantly cleaning itself. A cloud of dust surrounding an object near the sun cannot last forever. It is under constant assault. The pressure of sunlight itself, radiation pressure, acts like a wind. It pushes against these tiny particles. It wants to blow them away, to disperse them into the void. So, the next logical question, the question that turns this from a static measurement into a dynamic puzzle, is how long such material can remain surrounding the object before solar radiation disperses it. If the dust is being blown away, but the glow remains constant, then the dust must be replenished. The object must be bleeding mass to maintain that halo. This is the heartbeat of the problem. We are looking at a flow rate, not just a total amount. Loeb explains that the physics here can be understood without complex formulas. It is intuitive. The farther the particles travel from the nucleus, and the more slowly the sun's light slows them down or pushes them back, the longer the glow remains cohesive. It is a balance of forces, gravity pulling in, radiation pushing out, and the initial velocity of the ejection. For 3I Atlas, based on its trajectory and its distance from the sun, this retention window is calculated to be about 1 month. Think about that time scale, 1 month. That is the lifespan of the glow we are seeing. The dust we see today is not the dust we see next month. It is a constantly refreshing shroud. This means that if 10 million kilograms of material are visible at any given moment, and that material is flushed out and replaced every month, the object must be losing material at a ferocious rate. It is not slowly shedding, it is hemorrhaging. This brings us to the first major checkpoint in our investigation. We have established the mass of the cloud, 10 million kilograms. We have established the lifespan of the cloud, 1 month. From these two variables, we can derive a rate, and that rate is where the story begins to diverge from the expected narrative of a standard comet. If 10 million kilograms disappear within that span, the object must have been losing material at a rate of about 3 kilograms per second. 3 kilograms every single second. Tick. 3 kilograms gone. Tick. Another 3 kilograms for the entire duration of its passage. This is the baseline we need to hold in our minds as we move forward. This is the dust budget of 3II Atlas. But is that a lot? Is it a little? To answer that, we have to compare it to something. We have to compare it to the other component of the mass loss, the gas. Comets are typically described as dirty snowballs. They release gas, and they release dust. Usually, these two things go hand in hand. The gas drags the dust off the surface. But when we look at the estimated rate of gas loss for 3I Atlas during its peak activity, we find a number that sits around 500 kilograms per second. Do you see the discrepancy? We have gas leaving at 500 kilograms per second. We have dust leaving at 3 kilograms per second. This contradicts what we previously thought about the behavior of active interstellar visitors. We usually expect a dusty, messy breakup, but here the dust accounts for less than 1% of the total mass flow. It is a ghost of a ghost. The object is incredibly gas-rich, but strangely dust-poor. Or rather, the ratio is heavily skewed. This ratio, this less than 1% figure, is not random. In astrophysics, ratios are fingerprints. They tell us about the recipe of the object. And this specific ratio resembles something very specific. It resembles the interstellar medium of the Milky Way galaxy itself. It looks like the background noise of the universe. But, and this is a massive but, there is a critical distinction that prevents us from just dismissing it as standard interstellar noise. We are standing at the edge of a cliff in the data. We have the mass. We have the rate. We have the ratio. But we haven't yet talked about the particles themselves. We assumed they were standard dust, but the data suggests they are not. And this is where the re-evaluation by Avi Loeb takes a turn that has left many in the community scrambling to check their own models. Because if the particles aren't what we think they are, then the object isn't what we think it is. As we prepare to delve into the microscopic analysis of these grains in the next segment, keep that image in your mind. A 10-kilometer sphere of light, shattered into 10 to the power of 18 fragments, bleeding into the dark at 3 kilograms per second. It is a signal, and we are just beginning to decode it. The headline number was just the hook. The real story is hidden in the size of the grain. As we established in the previous chapter, the numbers surrounding 3I Atlas are not just data points. They are clues to a crime scene. We have a body, or rather, the ghost of a body, that shed 10 million kilograms of material. We have a timeline, a retention window of roughly 1 month. And we have a rate of loss, 3 kilograms every second. But numbers in isolation can be deceiving. To truly understand what 3I Atlas is, we have to look beyond the amount of material and look at the kind of material. We have to interrogate the dust itself. When we say dust in an astronomical context, your mind likely jumps to the dust on a bookshelf, or the sand in a desert. But cosmic dust is usually something far more ethereal. In the vast empty spaces between stars, the interstellar medium, dust is typically smoke. It is composed of particles so incredibly small that they behave almost like a gas. We are talking about submicron particles, jagged little clusters of silicates or carbon that are smaller than the wavelength of visible light. This is the standard fog of the galaxy. It is the stuff that obscures our view of the galactic center. It is the stuff that makes up the dark lanes in the Milky Way. So, when astronomers first looked at the brightness data from 3I Atlas, the initial assumption was that we were dealing with this standard garden-variety cosmic smoke. It is the safe bet. It is the default setting for the universe. But here is the crucial detail that Avi Loeb's analysis brings to the forefront. If 3I Atlas were shedding standard, submicron interstellar dust, the numbers wouldn't add up. The brightness wouldn't match the mass. The physics of the reflection would be wrong. To get that specific intensity of glow, that specific 10-kilometer mirror effect we discussed, from a total mass of 10 million kilograms, the particles cannot be microscopic smoke. They have to be larger, significantly larger. The derived size of the grains implied by the data is not in the realm of cigarette smoke. It is in the realm of sand. We are talking about particles that are perhaps a few microns across, maybe even larger. Now, microns still sound small to us. A human hair is about 70 microns wide. So we are still talking about something invisible to the naked eye. But in the scale of astrophysics, the difference between a submicron particle and a multi-micron particle is the difference between a pebble and a boulder. It is a massive leap in scale. It implies a completely different formation history. You don't get large grains like that from the wispy vacuum of open space. You need a factory. You need an environment capable of clumping atoms together, layer by layer, over millions of years. This contradicts what we previously thought about the nature of interstellar objects. We assumed they would be coated in the primordial soot of their journey, but 3I Atlas seems to be shedding something more substantial. It is shedding grown dust. Let's pause and visualize this. Imagine you are floating in space, watching this object pass. If it were shedding standard interstellar dust, it would look like a faint, bluish haze, scattering light in a very specific way, much like cigarette smoke scatters sunlight in a sunbeam. But 3I Atlas didn't look like that. The reflection suggests a cloud of distinct, solid grains. If you could reach out and catch some in your hand, you wouldn't feel a smear of soot. You would feel a grit. You would feel the texture of a world that was either destroyed or never finished. This size discrepancy is the key that unlocks the origin story. Why? Because large dust grains are heavy. They are harder to push. Remember the solar radiation pressure we mentioned? The wind of light? That wind blows tiny particles away very easily. It clears the smoke instantly. But it struggles to move the rocks. The fact that these particles lingered, forming that cohesive glow for a month, reinforces the idea that they have substance. They have inertia. They are fighting the light. So, what does this actually mean? It means that the 10 million kilograms of material isn't just waste. It is a sample of the object's internal structure. If you strip the paint off a car, you see the steel. 3i Atlas was stripping off its outer layers, and what it revealed underneath was not the fine powder of deep space, but the coarse grit of a planetary environment. This leads us to a fascinating comparison. We know of one place where dust grains of this specific size and composition are common. We see them in our own solar system, in the zodiacal dust bands, the debris left over from asteroid collisions and cometary breakups. But we also see them in a much more distant, much more ancient setting. We see them in molecular clouds. Molecular clouds are the stellar nurseries of the galaxy. They are the cold, dense wombs where gas collapses to form new stars. Inside these clouds, the density is high enough that atoms can stick together. They freeze onto dust grains, creating icy mantles. They collide and merge, growing from smoke into sand and from sand into pebbles. This is the first step of planet formation. It is the accretion phase. The fact that 3i Atlas is shedding dust that matches the size profile of material found in molecular clouds is a smoking gun. It suggests that this object is not just a random rock ejected from a dead system. It might be a pristine fragment from a system that was just being born. It might be a planetesimal, a baby planet, that was kicked out of its nursery before it could grow up. Think about the tragedy of that for a second. We are looking at a seed that never got to become a world. It formed in the dark, dense heart of a molecular cloud, gathering mass, growing its dust grains, preparing to join a planet. And then something happened. A gravitational interaction, a passing star, a chaotic orbit. Something ejected it. It was cast out into the void, frozen in time, carrying the signature of its birth environment across light years of empty space. And now it passes us, and as it warms up near our sun, it begins to shed that ancient skin. It releases those frozen, oversized dust grains, lighting up like a beacon. It is showing us its pedigree. It is saying, I am not from the empty space. I am from the places where worlds are made. This realization forces us to reevaluate the less than 1% ratio we discussed earlier. Remember, we said the dust accounts for less than 1% of the mass flow, while gas accounts for the rest. In a mature comet, we might expect a lot of dust. But in a primitive object from a molecular cloud, that ratio makes more sense. It is dominated by the volatile ices, the gas that froze onto those grains. The structure is fluffy, icy, and fragile. It is exactly what you would expect from a stellar nursery fragment. We are building a profile here. We have moved from a simple brightness measurement to a mass calculation, and now to a structural analysis of the dust itself. We have gone from it's bright to it's made of large, primitive grains from a star-forming region. The narrative is tightening. But there is one more layer to this physics puzzle. We have talked about the dust. We have talked about the gas. But we haven't talked about the motion. If this object is indeed a fluffy, icy fragment from a stellar nursery, how did it survive the journey? How did it hold itself together against the tidal forces of interstellar travel? And why, when it got close to the sun, did it not simply disintegrate completely? The fact that it shed mass at 3 kilograms per second is significant, but the fact that it survived to shed that mass is even more so. In the next chapter, we are going to look at the physics of survival. We are going to ask how a fragile object, bleeding mass, and fighting solar radiation manages to maintain its integrity. And we are going to see how this specific combination of gas and dust might explain the most controversial aspect of 3I Atlas, its acceleration, because, as it turns out, the dust isn't just a reflector. It might be part of the engine. But before we move on, I want to hear from you. We are dealing with scales that are hard to imagine, dust grains the size of bacteria, clouds the size of cities, distances measured in light years. Does the idea of a failed world or a planetary seed change how you view these visitors? Do you see them as rocks or as fossils? Leave a comment below with your thoughts on the stellar nursery theory. I'll be reading through them after the broadcast. Now, let's turn our attention to the forces that tried to destroy 3I Atlas and how it fought back. We are deep into the autopsy of a ghost. We have established that 3I Atlas was a visitor that shed 10 million kilograms of material, and that this material was composed of unusually large, primitive dust grains, the kind you find in the stellar nurseries where planets are born. But to fully understand the nature of this object, we have to look at the clock. We have to look at time. In astrophysics, time is often measured in billions of years, but for 3I Atlas, the critical time frame is much shorter. It is a matter of weeks. This brings us to one of the most elegant parts of Avi Loeb's analysis, the concept of the retention window. When an object ejects dust, that dust doesn't just sit there. It is immediately subjected to the violence of the solar environment. The sun is not just a light bulb, it is a cannon. It fires photons, particles of light, outward in all directions. When these photons hit a dust grain, they transfer momentum. They push it. This is called radiation pressure. At the same time, the sun's gravity is trying to pull that grain back in, and the grain itself has the initial velocity from when it was ejected from the comet. It is a three-way tug-of-war, and the result of that war determines how long the dust stays close enough to the object to contribute to the glow we see from Earth. If the dust is blown away instantly, the glow would be faint and fleeting. If the dust is heavy and slow, it might linger for years. Loeb explains that the physics here can be understood without complex formulas. It is a matter of geometry and speed. The farther the particles travel from the nucleus, and the more slowly the sun's light slows them down, the longer the glow remains cohesive. For 3I Atlas, based on the size of the grains we discussed in the last chapter, those large, heavy pebbles, and the intensity of the sunlight at its distance, this retention window is calculated to be about 1 month. 1 month. That is the refresh rate of the object's appearance. This number is the linchpin of the entire mass calculation. If the retention window were a year, the loss rate would be tiny. If it were an hour, the loss rate would be catastrophic. But at 1 month, we can do the math. If 10 million kilograms of dust are visible at any one time, and that dust is cleared out every month, then the object must be replenishing it at a rate of roughly 3 kilograms per second. 3 kilograms per second. Imagine a shovel tossing a load of dirt out the window every single second. That is the dust loss, but here is the crucial detail. That number, 3 kilograms per second is meaningless unless we compare it to the other thing the object is losing. Gas. Comets are volatile. As they heat up, ices turn to gas in a process called sublimation. This gas jets out, and it is usually what drags the dust with it. For 3I Atlas, we have estimates of the gas production rate during its peak activity. That number is around 500 kilograms per second. 500 kilograms per second of gas. 3 kilograms per second of dust. Do the math. The dust accounts for less than 1% of the total mass flow. 99.4% of what this object is losing is gas. Only 0.6% is dust. This is an incredibly clean exhaust. If you were to watch 3I Atlas up close, you wouldn't see a dirty, soot-filled plume like a coal plant. You would see a massive, invisible jet of pure gas sprinkled with a very sparse, very coarse grit of large grains. It is a gas-rich, dust-poor object. Why does this matter? Because this specific ratio, this less than 1% dust fraction, is not something we typically see in the comets of our own solar system. Our comets are usually dirtier. They have more dust per kilogram of gas. But there is one place in the universe where this specific ratio, gas dominating dust by a factor of 100, is the standard. That place is the interstellar medium of the Milky Way. The space between the stars is not empty. It is filled with a tenuous soup of hydrogen and helium gas, sprinkled with a tiny amount of dust. The ratio of gas to dust in the general mix of our galaxy is roughly 100:1. This connects to what we discussed in the previous chapter about the stellar nursery. If 3I Atlas has the same gas-to-dust ratio as the raw material of the galaxy, it reinforces the idea that it is a pristine fragment. It hasn't been processed. It hasn't gone through the cycles of melting and differentiating that happen inside a large planet. It is a raw sample of the galactic soup, frozen into a solid block. It is as if someone took a scoop of the Milky Way's molecular clouds, froze it, and threw it at us. This physics of survival tells us a story of resilience. Here is an object made mostly of frozen gas, likely hydrogen, nitrogen, or carbon monoxide, holding itself together through the deep freeze of interstellar space. It enters our system, heats up, and starts to evaporate. The gas screams off the surface at 500 kilograms per second. But the dust, those large, heavy grains, reluctantly lets go, drifting away at a mere 3 kilograms per second, creating a halo that lasts just long enough for us to measure it, before being swept away by the solar wind. The fact that the dust is so sparse yet so large suggests a specific formation history. In a typical protoplanetary disk where planets form, dust grains collide and stick. They grow, but if they grow too big, they fall into the star. If they stay too small, they get blown away. The grains on 3I Atlas are in that Goldilocks zone of early growth. They started to merge. They started to become pebbles, but the process was arrested. The system died before it could be born. And this brings us to the edge of the scientific data and into the realm of narrative implication. We have analyzed the light. We have weighed the dust. We have clocked the speed. We have checked the ratios. Every single metric points to the same conclusion. 3I Atlas is a fossil from a failed planetary system. But if it is a fossil, what kind of world would it have become? And if it came from a stellar nursery, are there more of them? The calculations suggest that for us to see one such object, the galaxy must be teeming with them. We might be swimming in a sea of frozen planetary seeds. In the next chapter, we are going to take these physical parameters, the large grains, the high gas ratio, the molecular cloud origin, and we are going to construct a profile of the foreign signature. We are going to ask what this object tells us about the environment it came from, and why its very existence challenges our understanding of how solar systems, including our own, are put together. We have looked at the how. Now we must look at the where. We have dissected the light. We have weighed the dust. We have clocked the gas. And now we must assemble these fragments into a coherent picture. The data from 3I on Atlas, the 10 million kilograms of shed mass, the large grain size, the gas-heavy ratio, points us toward a singular, startling conclusion. This object is not a random piece of space debris. It is a refugee. If the dust grains are indeed the size of pebbles, and if the composition matches the raw material of a molecular cloud, then 3I Atlas is likely a planetesimal. This is a specific term in astrophysics. It refers to the building blocks of planets. It is the stage between a dust bunny and a world. Imagine a stellar nursery, a vast cold cloud of gas and dust light years across, collapsing under its own gravity. Inside this cloud, stars are igniting. Around those stars, disks of material are swirling. In those disks, dust is sticking together, forming clumps. Those clumps merge to form rocks. Those rocks merge to form boulders, and those boulders merge to form planetesimals. In our own solar system, this process happened 4.5 billion years ago. Most of those planetesimals smashed together to build the Earth, Mars, Jupiter. Some were left over and became the asteroid belt. But many, trillions of them, were violently ejected. As the giant planets like Jupiter migrated, their gravity acted like a slingshot. They kicked these baby worlds out of the nest, flinging them into the dark void of interstellar space. 3I Atlas appears to be one of these exiles, but it is not from our nest. It is from a foreign system. So, what does this actually mean? It means that when we look at this object, we are looking at a timeline that runs parallel to our own. Somewhere, in a different corner of the Milky Way, around a different star, a solar system was trying to form. And just like ours, it was a violent, chaotic process. 3I Atlas was there. It witnessed the birth of that system. It carries the chemical signature of that specific molecular cloud, the specific mix of isotopes and elements that existed in that region of the galaxy. And then it was cast out. It has likely been drifting for millions, perhaps billions of years. It has crossed the unimaginable gulf between stars. It has passed through the emptiness where the temperature hovers just above absolute zero. And throughout that entire lonely journey, it held onto its cargo. It held onto those 10 to the power of 18 particles of dust. It held onto the frozen gas. It preserved the record of its birth until it met our sun. The heat of our star woke it up. It began to shed its layers. It began to tell its story. The foreign signature we are detecting is not just a chemical one. It is a narrative one. It tells us that the process of planet formation, the process that created us, is universal. It is happening everywhere, and it is messy everywhere. The galaxy is full of these shards, these failed worlds, these wandering seeds. But there is a deeper layer to this mystery. If 3I Atlas is a planetesimal from a stellar nursery, it implies that the environment it came from was rich in the heavy elements needed for life. The large dust grains suggest a high metallicity, an abundance of elements heavier than hydrogen and helium. This is the stuff of rocky planets. This is the stuff of biology. We are not just looking at a rock. We are looking at the potential for a world. If 3I Atlas had stayed in its home system, if it hadn't been kicked out, if it had merged with a few billion other planetesimals, could it have become an Earth? Could it have become a home? We will never know. That potential was frozen and cast adrift. This realization shifts our perspective from the scientific to the existential. We often look at the sky and wonder if we are alone. 3I Atlas suggests that the ingredients for systems like ours are common. The galaxy is manufacturing these building blocks on an industrial scale. But it also shows us the waste. It shows us the leftovers. For every Earth that forms, how many 3I Atlas objects are ejected? How many potential worlds are lost to the void? The data suggests the number is astronomical. Some estimates imply there are quadrillions of these objects drifting in the Milky Way. We are floating in a sea of them. 3I Atlas just happened to be the one that got close enough for us to see the glint of its dust. As we close the file on the astrophysics of this object, we are left with a picture that is both beautiful and melancholic. We have a traveler from a stellar nursery, shedding its ancient skin as it passes a foreign star, leaving a trail of 10 million kilograms of breadcrumbs that lead back to a home it can never return to. But the story of 3I Atlas doesn't end with the data. In fact, the most significant part of this event might not be what we learned about the object, but what the object forced us to ask about ourselves. In the final chapter of this investigation, we are going to step away from the telescope and look at the human response. Because in the end, science is not just about measuring the universe. It is about how we relate to it. And sometimes, the most important data point is the one that can't be plotted on a graph. We have spent the last 4 chapters dissecting the physics of a visitor. We have calculated its mass, timed its decay, analyzed its dust, and traced its origin back to a stellar nursery light years away. We have turned 3I Atlas into a set of numbers: 10 million kilograms, 3 kilograms per second, 10 kilometers of reflectivity. We have done what science is supposed to do. We have quantified the unknown. But there is a danger in quantification. Sometimes, when you reduce a mystery to a math problem, you lose the essence of the encounter. You lose the feeling of standing on the shore and watching a ship pass in the night. The most unexpected turn in Avi Loeb's analysis of 3I Atlas comes not from the astrophysics, but from the tone. It comes in the footnotes, in the correspondence, in the way the paper closes. It steps away from the equations and addresses the fear that often accompanies the unknown. Loeb shares a piece of correspondence he received during the height of the 3I Atlas interest. It was a letter from a young girl named Ariana. She had watched an interview where scientists were debating the nature of the object. Was it a comet? Was it an asteroid? Was it artificial? The debate was heated, the language technical and aggressive. Ariana wrote to ask a simple, piercing question. She asked whether 3I Atlas could be something bad. She asked whether the unknown should be feared. It is a question that resonates with anyone who looks up at the dark. We are hardwired to fear what we don't understand. When we see an anomaly, our instinct is to categorize it as a threat or a resource. We want to know what it is so we can know what to do. Loeb's response to Ariana is perhaps the most important takeaway from this entire event. He wrote back that science begins not with knowledge, but with accepting its absence. He told her that the unknown is not a source of fear, but a source of wonder. Those who fill themselves with certainty, those who decide in advance what an object must be, lose the ability to see what it is. Those who question, those who admit they don't know, continue to see. And so today, December 27th, 2025, as we look back at the data, the subject at hand is not simply a comet. It is not simply a planetesimal from a molecular cloud. It is an object that crossed our world, left behind dust, calculations, questions, and then vanished without explanation. We have a theory about the dust. We have a theory about the origin, but we do not have certainty. We never touched it. We never brought a sample back to a lab. It is gone. If 3I Atlas holds any true significance, it is not in the mass it shed, but in the uncertainty it left behind. That uncertainty is valuable. It is more valuable than any hard data point because it forces us to remain humble. It forces us to look upward, not for romance, but for understanding. It forces us to admit that our models are incomplete, that our categorization of the universe is a work in progress. The 10 million kilograms of dust are dissipating now, scattered by the solar wind, joining the background noise of our own solar system. The glow has faded. The object is racing back into the deep freeze, carrying its secrets with it. But it has left a mark on us. It has reminded us that the galaxy is a dynamic, exchanging place. It has reminded us that we are not isolated. And it has reminded us that sometimes the most scientific thing you can say is, "I don't know, but I want to find out." As we close this deep dive, I want to ask you to do one thing. If you found value in this journey, from the brightness of a reflection to the philosophy of the unknown, please hit the like button. It helps us bring more of these deep analytical stories to the surface. And tonight, if the sky is clear, go outside. Look up. You won't see 3I Atlas. It's too faint, too far. But look at the space between the stars. Think about the dust that is floating there. Think about the seeds of worlds that are drifting in the dark, waiting for a star to wake them up. And ask yourself what else we failed to notice while it passed, silently right in front of us. Good day, and keep looking up.